Hi everybody, welcome back. So in this video we're going to start a new chapter on confidence intervals. And this is significant because we're finally getting to the inferential part of inferential statistics. So we studied how things are distributed and sample means are distributed, and the probabilities that a sample mean is in a certain range. Now we're going to actually use that to make inferences about a population mean when it's not known, okay, or other parameters that they're known when they're not known. And we're going to do this first by using confidence intervals, and then we'll do some hypothesis testing in the next chapter. So so if we're assuming that we're going to first talk about confidence intervals for the mean. And let me just tell you, there are two estimates going on here. One is when we take a sample mean and we use that to estimate the population mean. That's an example of a point estimate, where you say something like, I'm guessing that the mean is equal to 5.73, equal to some very specific number. Then there's an interval estimate, where you say, I'm guessing the mean is between 5 and 6, or some two numbers, or some range. And what we're going to be using both point estimates and interval estimates. We're going to use the sample mean, x bar, as a point estimate for the population mean, or mu. And then what we'll be doing is, from that, we're going to build an interval around x bar, and we're going to say, I think that the population mean is in here. Maybe we don't really want to say it's exactly equal to this number, because that statement's probably going to be wrong. But it could be if we say that the population mean is between these two numbers, that's more likely. We have a little more confidence in that, and that's why we call these intervals confidence intervals. So let me just say that the x bar, the sample mean, is what we call an unbiased estimator. Don't worry about the definition of unbiased too much, but let's just be, what it means is the expected value of x bar is mu, which is exactly what we want. So so we use x bar as a point estimate for mu. We build an interval around x bar, and that means we're talking about an open interval where we have x bar minus a number and to x bar plus a number. And let me just remember, in the interval notation, this just represents all the numbers that are greater than the left endpoint and less than the right endpoint. Okay, we use parentheses because we're not including the endpoints. There's really no need to include these points when you're talking about a continuous random variable. Okay, so what we're saying is, so we have this this number e sub c. And obviously that we're going to get a different interval for every value of e sub c. This interval, starting with x bar minus e sub c and x bar plus e sub c, is called a confidence interval for mean mu, and it's actually called a C confidence interval, where C is the level of confidence that the mean is in this interval, that the population mean is in this interval. So we call E sub c is the margin of error, and you probably heard of that term before, even before this course, when they talk about certain polls or surveys in the news, and they say, oh, this is within the margin of error, or something like that. We're going to be talking about that as well, but by right now we'll interpret the margin of error as the half the length of this interval. So it's like we're saying with C confidence, confidence level C, that mu is in this interval, that mu is within E sub c of x bar, or x bar is within E sub c of mu. It's actually the same thing, right? So so that's the margin of error, and again, the margin of error is exactly half the distance of this interval. Now the question, of course, becomes, how do we compute the margin of error? Okay, that's the whole point. Well, it's going to be different in different cases, and this section focuses on the first case, where we make two main important assumptions. First is we're assuming that the population is either normally distributed or the sample size is at least 30. And then the second assumption is that sigma, the population standard deviation, is known. If we meet these two, if these two assumptions hold, then E sub c is calculated this way, as this number is Z sub c times sigma divided by the square root of n, where n is the sample size. Now, what is this Z sub c? Well, Z sub c is we call it a critical value, and we define it this way as one of the boundaries, the right boundary of this region here, where we start with a standard normal curve, and then we have this middle area whose area is exactly c, and then Z sub c and minus Z sub c are the boundaries. And the way we can calculate this is, we could calculate this as using our inverse norm, okay, because the inverse norm of this area right here would give us minus Z sub c. So that's why we have a minus here. In reality, though, c is usually either 0.90 or 0.95 or 0.9 or 0.99, in which I'll give you the values of Z sub c in a moment. Okay, so you don't always have to use the inverse norm, because it's basically, this Z sub c is only going to be about, maybe have just 3 or 4 values you really have to know. So if we have that, then this is how the margin of error is computed, and then this would be our confidence interval, right? Now let me just show you that the first assumption is very important, because that ensures that the sample means have a normal distribution. That's why we are allowed to use this this curve. Okay, and then, well, if sigma is known, then it just helps us out. Now it's kind of strange. Well, why would sigma be known and not mu? Well, let's just assume. Let's just go with this. Okay, it might be that we might know sigma from another calculation, okay, or from, maybe it's been a couple of years and maybe we're actually guessing that sigma is something. All right, right now let's not worry about that. We'll see there are going to be some cases where we can actually replace sigma with the sample standard deviation, but that's in the next section. So I want to show you why this works. Okay, I give you this formula. Why does it work? So we're going to do a little bit of algebra here, and I want you to, this next part, it's not going to be on the test, but hopefully you just see where this is coming from. Okay, so we recall that because we've assumed that we know that the sample means have a normal distribution, and it's that distribution is mu, and the standard deviation of the sampling distribution is sigma divided by square root of n. Okay, so we got this from the central limit theorem, in the last chapter. So we have this random variable z defined this way, and this has the standard normal distribution. Well, what that means is the probability that z is between these two numbers is exactly c. So that's how we get this part. All right, so this just comes from the central limit theorem. Now we just do a little bit of algebra. We multiply, but actually not even algebra necessarily. It's just some basic math. We multiply both sides of these inequalities by sigma over square root n. Okay, we can do that. That does not reverse the directions of the inequalities because we're multiplying by a positive number. Then what we can do is we can say, what we can do is we can multiply everything in here by -1, and if we do that, then this becomes mu minus x bar, and then this minus becomes a plus, and this has a minus, and these things are reversed. But then if we rewrite them again, we get this. Another way of thinking about this is, well, this is going to be the opposite of this, all right? So if some number is between, let's say, -5 and 5, then its opposite is also going to be between -5 and 5. All right. So hopefully you can see that this and this are equivalent. And then from here we can add x bar to both sides, all three sides. And we're saying that mu, so now we get that mu is bigger than this number and less than this number. But this number is z sub c sigma over square root of n. That's precisely e sub c. Okay, so we get that this inequality is equivalent to this inequality. Okay, and so we're really saying, your book says it's incorrect to say the probability that mu is between this number and this number is equal to c. But essentially, that's what we're doing. Okay, what we would say in your book says we say with C, confidence level C, or with C% confidence that mu is is in this interval. Okay, that's what we would say. But all right, so that's why this works. Okay, and that's why we say C is our confidence level, because the probability that mu is in this range is exactly C. All right, now before we go on to the next part, let's do a few examples here of how this might work. If we go on to page 3, example 1, let's say we have a situation where sigma is known, it's 1.5. We take a sample of size 40 and get a sample mean of 12.3. And let's say we want to find a confidence interval for mu, and as well as the margin of error. We already, since n is bigger than 30, we already have that first assumption taken care of, and we're saying sigma is known, it's 1.5. So we can go ahead and proceed. So what we want to do is, given c, let's find what z sub c is. And z sub c, this is going to be the inverse norm of, I guess it would be 0.05. Let me just tell you what it is. This is 1.645. Okay. And let me tell you the other values. If z is 0.95, z sub c is 1.96. And if c is 0.99, z sub c is 2.575. Okay, memorize these three values because almost all the others are going to be the same. The one exception is if you have if c is equal to 80, I'll just tell you that z sub c is 1.282. But we won't use this too many times because really when you don't want to announce to your say to your employer, oh, I'm 80% confident that this is true. No, you'd like a confidence level in the 90s. So we usually use these three numbers. Okay, then for part A, if C is 0.90, C sub C is 1.645, and so E sub the margin of error would be 1.645 times 1.5 over the square root of 40. Okay, and this would be 0.390. Which is we're going to round this off to 1 decimal place to make this 0.4. And the reason why we use 1 decimal place is because that's what we have for our sample mean. Okay, our sample mean uses just 1 decimal place. And in general, the rule is you use the same number of decimal places that your sample mean is. Okay. All right. So then x bar is 12.3. If we compute 12.3 plus 0.4, that would be 12.7. If we take 12.3 minus 0.4, this would be 11.9. Okay, and so our interval would be, the left endpoint would be 11.9, and our right interval would be 12.7. So what we're saying is we could state with 90% confidence that mu is in this interval. If we do the same thing with when c is 0.95, then the margin of error, by the way, the margin of error in this last example would be 0.4. Here the margin of error would be 1.96 times 1.5 over the square root of 40. And this would be approximately equal to 0.465, which we round to the round up, and so this is we round to the nearest number, which is 0.5. Okay. So that's our margin of error. We take 12.3 plus 0.5 is 12.8. 12.3 minus 0.5 would be 11.8. And so our confidence interval would be 11.8, 12 point. Now notice that this interval is slightly wider than this one, and that's because if you want a bigger confidence interval, you have to, if you want to have a bigger confidence level, you need a wider interval. Okay. And then if we use C with 0.99, E sub C is going to be 2.575 times 1.5 divided by square root of 40, and this is approximately 0.611. We can round to say this is approximately 0.6. So that's our margin of error. Again, we take 12.3 plus 0.6, 12.3 minus 0.6. This is 12.9. This is 11.7. So our interval would be 11.7, 12.9. All right. Now I will let you, it will finally, if we would do this for 80% confidence, E sub C would be 1.282 times 1.5 over the square root of 40. Okay. And I think that's going to be approximately 0.3. Okay. And so this would be, we take 12.3 plus 0.3, 12.3 minus 0.3. So our interval would be 12.0 and 12.6. Okay. And of course this is the smallest confidence interval, but also has the smallest confidence level. All right. So I'll let you maybe skip to example 3, and I'll let you do that before we do the next video. Okay, so I'll see you at the next video.